Welcome to Podcast Learn and Fun. Ever think about how, mathematicians would take two different ideas, a flat map and a 3D model, and then somehow combine them and create something even bigger, more complex?
Yeah.
That's where this idea of tensor products comes in. They're this really powerful tool that shows up everywhere from, linear algebra to quantum mechanics and even machine learning.
It's really cool how they work. Like imagine instead of just like multiplying vectors the way you did in school, you're creating this whole new structure that has information from both of the original vectors. So it's kind of like if you were weaving together threads from two different fabrics and you make something totally new.
Okay, so we're not just smashing things together. We're kind of
Yeah.
carefully, intertwining them. But how do we represent this mathematically? It sounds really abstract.
So we have this special symbol and it basically acts like a connector to bring together two objects. And that could be vectors, matrices, even more complex things.
Got it. But now I'm curious, what kind of space does this new combined object live in? It can't be in either of the original spaces, right?
You're right. It lives in a brand new space, and it's called the tensor product space. And this new space, it's not just a bigger version of the old ones. It's a space that's made specifically to hold these combined objects.
So are we saying this new space can have, more dimensions than either of the original ones? How does that even work?
So think about it like building with Legos. Say you have a set of 2D Legos and a set of 3D Legos. You can combine them together and build structures that aren't just 2D or 3D, but something much more, richer and more interesting. So the tensor product space is kind of like that. It gives you the framework for building these more complex objects.
Okay, that's helpful. But how do we actually build this new space? What are the Legos in this mathematical world?
Okay, so just like a house needs bricks, we need building blocks for this new space. And those building blocks are the basis vectors from our original spaces. So if we combine all the possible pairs of basis vectors, we get a foundation for our tensor product space.
So if one space had two basis vectors and the other had three, the tensor product space would have six.
Exactly, you got it. And now you've created a six-dimensional space from two smaller ones.
Whoa. I'm starting to see how powerful this is. But all this talk about basis vectors and dimensions is making my head spin a little bit. Can we walk through a specific example to make it more concrete?
Sure, let's keep it simple. Imagine a two-dimensional space like a flat sheet of paper. That's our first space. Then we have a three-dimensional space like the room you're sitting in.
Okay, I'm picturing it. So how do we combine those spaces?
We take all the possible combinations of the basis vectors. In this case, we'd have six of them. It's like taking each direction on your sheet of paper and then combining it with each dimension of your room, like up and down, left and right, forward and back.
So we end up with six unique directions in this new combined space. But what would an actual element in this space look like? Can we build one?
Okay, so let's take the diagonal direction on your sheety paper, and then let's combine that with the direction in the room that goes up and to the right. And now we've created a specific element in the tensor product space that represents a combination of those two directions.
Okay, I think I'm starting to see how this works. It's like we're taking pieces from each space and we're weaving them together to create something new and much richer. This is blowing my mind a little bit.
Yeah.
Why go through all this trouble? Where does this tensor stuff actually show up in the real world?
Oh, you have no idea. This is where it gets really exciting. So for example, imagine trying to describe the state of two entangled particles in quantum mechanics. So
Okay, entangled particles. I've heard about that. It's like they're connected even when they're miles apart, right? But how do tensor products help us understand this?
that's the really cool thing about them. Tensor products let us describe the combined state of the particles in a way that really captures their interconnectedness. It's not just about describing each particle individually, it's like representing their relationship as one thing.
So it's like the tensor product is saying that these particles are more than just the sum of their parts. Like they have this weird connection, and we need a special tool to describe it.
Exactly. And because the tensor product space is built from all the combinations of individual states, we can actually represent entangled states that wouldn't exist if we only looked at the particles separately.
Wait, are you saying we can create states that are totally new? Like states that don't belong to either particle on its own?
Yeah.
This is getting weirder.
Yeah, that's the magic of quantum mechanics. The tensor product gives us this mathematical language to describe these strange connections.
Okay, my mind is officially blown. But before we go too far down the quantum rabbit hole, I remember you mentioned something called bilinearity earlier. What does that even mean, and why is it important for tensor products?
Okay, so bilinearity basically makes sure that the tensor product behaves well with addition and scalar multiplication. It's like having rules that guarantee things will work out consistently no matter how we combine the elements.
So it's like a mathematical safety net, making sure everything plays nicely together in the tensor product space.
Yeah, exactly. It's super important because it lets us do calculations and, manipulate the tensor products in a way that makes sense.
That makes sense. But you also said something about tensor products being distinct even if their components are combined differently. I'm a little confused about that. Can you explain that?
Okay, sure. Let's say you're combining two vectors. One represents the direction north, and the other represents the color blue. So the tensor product of north and blue is different from the tensor product of blue and north.
Wait, so the order matters.
Yeah.
It's not like regular multiplication where 2 times 3 is the same as 3 times 2.
You got it. In tensor products, the order and the specific elements we combine really matter. It's about capturing the deeper relationship between the objects, not just their product.
Okay, so it's not just about mixing colors. It's about understanding the specific way they're mixed. That makes sense. But I'm still struggling to see why all of this is so important. Can you bring it back to the real world again?
Okay, so think about machine learning. It relies a lot on analyzing these huge data sets. Well, tensor products give us a powerful way to represent and manipulate this data, and that allows us to uncover hidden patterns and make predictions.
So you're saying all the data we make every day, from online shopping to social media, can be represented using these tensor things?
Absolutely. And then by using techniques like tensor decomposition, we can break down complex data into simpler parts, and that makes it easier to understand and get insights from.
That's incredible. So tensor products aren't just helping us understand the quantum world, but also help us understand all the data we make every day.
Exactly. But we've only just started. There's so much more to discover about tensor products, from their applications in geometry to their role in, shaping the future of artificial intelligence.
I'm still blown away that tensor products are used for everything from quantum entanglement to analyzing data.
It really is amazing, and it gets even more interesting the deeper we go. Remember how we talked about machine learning using tensor products to represent data? Let's go a little deeper with that. Imagine trying to recommend a movie to someone based on their past ratings.
Okay, so we have all this data about what movies people like and dislike. So how do tensor products help us make sense of all of that?
So think of all those ratings as this giant multi-dimensional grid, and each dimension represents something like, a user, a movie, a genre, even what time of day they watched it. And this grid is like a tensor, and it captures all those relationships.
So we're not just looking at individual ratings, we're looking at the whole picture across all these dimensions. It's like a giant map of movie taste.
Exactly. And this is where tensor decomposition comes in. It lets us take that massive tensor and break it down into smaller pieces. And that helps us see what's driving those preferences.
So instead of looking at millions of ratings, we're finding the underlying things, like whether someone prefers comedies or action movies, or if they like to watch movies late at night.
Exactly. And once we understand those factors, we can use them to predict what other movies that person might like, even if they haven't rated those movies yet.
That's so cool. It's like we're figuring out this secret code of movie preferences.
Hmm.
But wait, we also talked about tensor networks before. Are those related to this data stuff?
They are, but in an even more mind-blowing way. Imagine you take those individual tensors that represent users or movies, and you connect them all together in this network. Kind of like a social network, but for data.
Okay, I'm picturing nodes that represent data points and then links that represent relationships between them. But why would we do that?
Because data in the real world is never isolated. A user's movie preferences could be influenced by their friends or their mood or even the weather. Tensor networks help us capture all those dependencies.
So it's we're going from this flat map of data to this, multi-dimensional web of connections. That's kind of making my head spin, but in a good way.
And this isn't just theory. Tensor networks are being used in all sorts of cutting-edge research, like quantum computing and AI.
So we've gone from combining simple vectors to building these complex networks that represent the whole universe. Tensor products are this universal language, right?
You got it. They're a fundamental tool for understanding and working with these complex systems. Everything from tiny particles to the networks that shape our world.
I've learned so much today. Tensor products are no longer just this weird symbol in my mind. They're the key to understanding all these amazing problems in science and technology.
It's been great exploring this with you. I wonder what amazing discoveries are waiting for us as we keep exploring the power of tensor products.
Thank you for listening to Podcast Learn and Fun. We hope you enjoyed the journey of learning. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.